Prior to the development of the concept of infinity during the 19th century, mathematicians such as Cantor, the concept of infinity has not fully been understood. It had often been a topic of study, and the intrigue it caused led to the paradoxes of Zeno. Infinity as a concept had been used throughout ancient Greece. However, the term did not find its most beneficial use until Newton and Leibniz developed calculus. When discussing the area under a curve, Newton's method was to approximate the area by forming rectangles either inscribed below or circumscribed above a curve. As the number of rectangles increases, the approximation would approach the true value of the area below the curve. This idea of infinity is incomplete. Cantor sought to explore this concept and came upon one of the most inspiring conclusions of mathematics. Cantor came to the somewhat simple and straightforward conclusion that two sets have the same number of elements if their elements can be matched up. Let's consider the set of natural numbers. This is often considered the most basic infinite set. We can fairly easily convince ourselves that this set continues without end. No matter how long you count, there's always going to be a larger number. Using this as his basis of infinity, he showed that other sets also contain an infinite number of elements. For example, the set of triangular numbers is infinite because the nth triangular number is given by the equation n times n plus 1 over 2. This not only tells us what the nth triangular number is, but it also shows us exactly what that one-to-one correspondence is between the set of natural numbers and the set of triangular numbers. Next, consider the even natural numbers. You may be led to believe that the set of even natural numbers contains fewer elements than the set of natural numbers because natural numbers could be either even or odd, and for every odd integer, there is an even integer. Although this makes intuitive sense, the set of even natural numbers is the same as the set of natural numbers. The same can be said of the set of odd numbers. So here we can see that the union of the two sets contains more numbers than either of the two sets, but also contains the exact same number of either of the two original sets. Consider the set of rational numbers. Surely this set contains more numbers than the set of natural numbers. Between any two natural numbers, there exists an infinite number of rational numbers. This just feels like a greater infinity. The trick here Cantor found was not in describing the rational numbers, but in finding a one-to-one correspondence between the two sets, and he did show that there is a one-to-one correspondence. Therefore, the size of the set of natural numbers is the same size as the set of rational numbers. Let's show how he found that one-to-one correspondence. First, let's make a table where the rows are denominators and the columns are going to signify different numerators. Here we have listed off each fraction which can be obtained by all the options for the numerator and denominator using whole numbers. We can follow suit likewise, where here we see a path that can be taken along the set of rational numbers in which not a single one will be missed. This makes us wonder, are all infinities the same? Cantor made use of the method of proof by contradiction to conclude that there are indeed different sizes of infinity. The next level, if you will, of numbers would be the set of real numbers. This contains the set of rational numbers, which we just showed was infinite, yet of the same size as the set of natural numbers, and the set of irrational numbers, which is the set of numbers which cannot be written as fractions. His proof would go something along the lines of this. Because Cantor in his discovery of different sizes of infinity, we now have a better understanding of the infinite and infinite processes.